So I need to share the screen, right?
Yeah. Yes.
Okay, thank you very much. My name is Suong Hoa. I'm a professor in the Department of Mechanical, Industrial, and Aerospace Engineering at Concordia University in Montreal, Canada. I'm also the director of the Concordia Center for Composites. And I've been working in composites for many years. Mainly these are the carbon epoxy, glass epoxy that have been used in making many components in aircraft, automobiles, or in the wind turbines. And recently I have heard about this 4D and 3D printing. So I thought maybe I can combine the composite material together with the 4D printing to make something, maybe something new. And so this is the first time that I attend this 4D printing and metamaterial conference organized by Jakajima. So it looks like an interesting conference. So first, I think I need to define a bit about what to mean by regular 4D printing and also to distinguish that from the 4D printing of composites. So I think that for people that attend this conference, everybody knows about 3D printing. And the picture on the left here is show you the process of 3D printing. That means you just use some kind of orifice with the material inside and you deposit layer by layer. And by controlling the motion of this orifice and also the amount of material, whether you deposit or you don't deposit, then you can make a complex structure. So this case here, then you can make a very complex structure, and there is a lot of application for this particular area. And from what I understand is 4D printing is that you utilize the same concept as 3D printing, except that in this case, you deposit different materials at different locations. For example, you have this location, you have one material, another location, you have another materials. And the response of these materials to the external stimuli, such as heat, electricity, light, moisture absorption, and things like this may be different. So by doing that, by having different materials at different locations here, by the time you finish making the layers here, then you subject that kind of layer to this activation process, such as heat, electricity, light, moisture, magnetic field, etc. And due to the fact that the response from these different materials to these activation mechanisms are different, so that way then the structure will change the configuration. That means the configuration change to a flat piece to some kind of a curved piece, and probably controlling the position of these and also the properties of the materials, you can really kind of come up with some kind of different shape that you wish. So what happened is that the case of the for the case of the 4D printing, what I found is that the material have fairly soft. Okay, usually people use some kind of soft plastic rubber or something like this. And for this case here, you can see that the modulus is about 10 GPa, and the strength is about 10 MPa. So basically, that's the case of the kind of soft materials. And what I feel is that we're going to do to distinguish that for the case of 4D printing of composite. And I mean, in this case here, rather than using the soft material, I think the last speaker talked about the biomaterial, something like the cellulose fibers, and they have some kind of properties. But compared to things that I studied, carbon epoxy, that means that these are the materials that have very high mechanical properties. The modulus is about 155 GPa, the strength is about 1,500 MPa. And so, like I said, these are materials that have been used in making component of aircraft, automobile, or wind turbines. So they are very stiff and strong. So that is one particular difference between the 4D printing of composite and the regular 4D printing. The second difference is that we use an automated fiber placement machine, which is a fairly large machine compared to the case you have the 4D, you have the 3D printer. Normally the 3D printer is fairly small. It can fit onto a desktop, and it can make some kind of a small components. But the automated fiber placement machine is a fairly large machine. It can be used to deposit layers additively to produce stack of composite layers. And these layers here consist not only just the resin, but also the fibers. These are continuous fibers. So that's the second kind of difference between the 4D printing composite and the regular 4D printing. The third difference is that rather than having the different materials at different positions along the stack of the deposition, we depend upon the anisotropic properties. That means that the change of the different properties along the different direction of the materials that give rise to the interaction between the layers, and that kind of the anisotropic property give rise to the change in the shape of the material. So by using these kind of things here like this, would be able to make structure complex geometry with good mechanical properties and using only flat modes. So saying a little bit about the anisotropic behavior. Now, anisotropic behavior, that means the properties are depending on the direction. For example, you take a look into one single layer of the composite, such as the case of the carbon epoxy here. Then you can see the blue lines, they represent the fiber. So these fibers are fairly small. Normally the diameter of a fiber is about 10 micron. Now the diameter of a hair, the hair that we have is about 100 micron. So that means that the diameter of this fiber is about 1/10 that of the diameter of a hair. So when people make the composite, they use a lot of these fibers. They have the very tiny fibers, and then around each of these fibers, you have some kind of epoxy resin. So epoxy resin, it can surround the surface, and the epoxy resin is used to bond many of these fibers together. So in this case, you can see the material consists of fiber and resin, and also the anisotropic property of this thing here is that it varies along the fiber direction and transfers to the fiber direction. So if you take a look along the fiber direction, normally it's very strong and stiff. Transfer to the fiber direction may not be. But one particular aspect that we are looking for in the case of 4D printing here is about the shrinkage. The shrinkage. That means that in this case here, when you heat or when you cool this material down, then along the fiber direction, it doesn't expand nor contract as much because of the fact that it's controlled by a lot of these stiff fibers. But transfer to the fiber direction here, then it expands and contract a lot. Okay, the expand and contract may be 100 times bigger along this the transfer direction than along this direction. So that is the case of anisotropic behavior of the layer. Now each of the layer has a thickness of about 0.13 millimeter. It's about 130 micron. So it is slightly a bit more than the diameter of a hair, and it's about the thickness of a sheet of paper. So you have these things here, very thin and very stiff and strong. And these are the basic constituent of the composite materials. Now you may wonder that, okay, suppose you have a thing like that, how do you make an airplane out of that? So the way the people make a structure is that they lay many of these layers together. For example, you can have a layer at 0 degree. You have another layer at 90 degree. You have another layer here at 45 degrees and minus 45 and so on. So that means that by stacking many of these layers together, then you can build up a structure. So 8 of these things can build up about 1 millimeter. So you have a structure of an airplane like a skin about 3 millimeter. You need 24 of these layers. So that's the way that people do that in the case of making airplane. Except that usually in airplane, they look only through the case of symmetric laminates. I mean, laminate that do not bend or kind of curve. In our particular case, we are looking into the deformation. So that means you take a look into one simple case, such as the case of a laminate here that consists of 0-90. So that means you have a laminate here consists of 2 layers. One layer below 0 degree orientation, you can see the fiber running along this direction here, and one layer above that along the 90 degree orientation. So we call it a laminate, a combination of 2 of these layers together. Now what happened in this case is that you have the layer at the bottom here along the 0 degree orientation. When you heat or you cool it, then it expands and contracts very little because of the fact that the fiber is stiff, but it expands and contracts a lot along this transfer direction. At the same time, you take a look into the second layer, the layer above, which is at 90 degree orientation. So along this way, that you can see that it expands and contracts a lot along so-called this X direction, but it expands and contracts very little along the Y direction. So when you put these 2 layers together, they bond. They bond together to make a single unit. Then when you either heat or cool it down, the fact that you have the difference in the degree of shrinkage or the degree of contraction along of this direction, and the interaction between these 2 layers here will make it curve. So this case here that you can make a curved structure from a flat mold. Now usually the way that people make the composite is usually because of it's made out of the epoxy resin. you have to bring it to high temperature, like 180 degrees centigrade, to cure it. That means you have to cure the resin to make the resin to change from a liquid state to a solid state. So at the beginning, you have something that is flat, and then you heat it up and you cure the resin. So when it's cured at 180 degrees centigrade, and after that, whenever the thing is rigid and bound together very well, then you cool it down. When you cool it down, then again, due to the fact that you have difference in expansion or contraction along the different directions, these will make a curve. It will curve up and make a curve structure. So basically, that is a 4D, the fourth dimension. The fourth dimension is the same that after you start with a flat layer, then after that you cool it down, then we give you the curve configuration. So that's basically the idea in terms of the mechanism behind the 4D printing of composite. It depends on the anisotropy, that means the difference in the properties along different directions to create the change in the shape of the structure. And at the beginning, you only need to have a flat mold. You lay everything down flat to begin with. So the next thing here, just to give you an idea what it means by an automatic fiber placement machine. So this one here, you'll show you a machine. Basically, it has a lot of complex things here, but it lay down. It has some kind of a tape of the thermoplastic to go down. And you can see that we lay that on some kind of a flat mandrel here. And right now we have the fiber along the 0 degree orientation. And what I show you right now is that the machine will lay down the fiber at 45 degree orientation. Okay, so that's basically the operation of the fiber placement machine. By controlling the machine, you can lay down the fiber at different orientation. And in this particular presentation today, we only look into the case where you have the 0 and 90 orientation of the fiber. So I want to show you a few applications that we have developed over the last few years. So that means that we have made what we call the S piece. That means the pieces that have the shape of an S. Then we also have made the composite flowers. I mean, the case where you have many petals that look like a flower. Then the composite leaf springs that has some kind of a good practical application because it has good stiffness and strength. And also the omega stiffeners, that is the case that we use in aircraft. So the case of S-shaped piece, what we do in this case is that, so we have two levels, level 1, level 2. Level 1, we have on the right-hand side, we lay down the one layer at 0 degree orientation. And on the left-hand side, we lay down layer at 90 degree orientation. At level number 2, we have layer on the right-hand side, we have a layer at 90 degree orientation. And on the left-hand side, we have a layer at 0 degree orientation. So basically by doing it like this, then you have on the left-hand side, you have a laminate. Laminate here that have the 0 degree on the top and 90 degree on the bottom. On the right-hand side, you have the layer 0 degree on the bottom and 90 degree at the top. So these are opposite to each other. So by the time you cool it down, then again, due to the fact that these different layers have different shrinkage, then this piece will curve like this. It will curve down, it will concave down, where this piece will curve up. So then basically you have a shape like an S. So that's what we have. So that means you begin, at the beginning, when you lay down, things are flat. And by the time that you finish making it, that you can have the different kind of pieces with the S shape. And you can have a different kind of, depending on the overlap here, that you can have different shapes if you wish. And another thing that we have done is that also we make this so-called the composite flower. You can see that you have, these are carbon epoxy, and you have many, you have 5 petals. You have the petal here at the center, it curves more than the next petal and the next petal and so on. So that be basically the same principle. It's the same that you use the 0-90, but you vary the thickness of each of these different petals. By the time you finish, cool it down, that you can have this particular shape. So that, again, this technique is unique in the sense that you cannot use the conventional method of manufacturing of composite to do this, because the conventional way that people make composite structure is that they have to make a mold. And they have to make a mold. So this case here, if you make a mold, you can only make a mold of one particular configuration. You cannot make a mold of several configurations. All right. So that means the mold can give you only maybe one shape, but not all of the five different kind of petals like this. So you can only do this using the technique of 4D printing of composite. Then we have another application, because when I show this presentation to people, they say, okay, that's impressive, but it looks like not very strong. Okay, you have maybe something like a shape, but you don't have the mechanical properties. So this case here, we were working, trying to see whether we can develop something that is stiff and strong and has some kind of good engineering applications. So we developed here, we call the composite leaf spring. Leaf spring. I mean, normally the leaf spring is the one that you use. People use it to support the automobile. Behind, underneath the car, you have the leaf spring that is supporting the weight of the vehicle and the vibration and things like that. So normally these are made of steel, some kind of metal. And the people have also used, they have made the composite spring using composite as well, except that what they have to do, they have to make a mold. So that means they have to make a mold of this kind of shape, that they have to lay the composite on top until they finish, and finally they have the piece. So that's okay. You can make the composite leaf spring using a mold. But again, in this technique, we use a 4D printing. It's the same that we don't need to have a mold of this complex shape. We start with something flat, okay? And then by the time you finish, you can have a piece. So this case here, this kind of a structure, we use the layup of 9036 or 024. So you have one layer of 36 layers of 90-degree orientation, and you have another 24 layers of 0-degree orientation. So by the time you do like that, we have a piece. You start with a flat piece, you end up with this. And so this is like a spring. Basically, hey, you can push it up and down, and they can have a springing action. And the spring constant, I mean, you get the load divided by the displacement here is 486 Newton per centimeter, which is equivalent to many of these practical springs that are being used right now. Now, the important thing that we have is that people may say, okay, yeah, fine, you can deflect that, but can it last? Can it really kind of fluctuate up and down a lot? So what we did is that we push this up and down from a curved configuration to flat, up and down 1 million times. Okay, 1 million cycle, up and down, from curve to flat, and then it did not fail. Okay, so after 1 million cycle, it's still running okay, no crack, no failure. So it shows that yes, we can make something that is fairly simple configuration without a mold. You can make a good practical structure that can be used in the practical applications. Then we move on and we did something else. I mean, at the same, have some kind of a complex configuration, such as the letter A. Okay, the letter A, B, C. So this is the layup sequence for the letter A. Okay, and by the time, so these are flat configuration. We exaggerate the kind of displacement, but remember, each layer here is only like a sheet of paper, 0.1 or 0.3 millimeter, the thickness of a sheet of paper. For example, 0.3, that means three layers. That means the thickness of this is about three sheets of paper. So it's very thin. And the way we show like this is to really show what is really happening at the micro level. But in reality, it's basically flat. And this is here, this is what happened at the end. After you finish, you finish it, and then it gives you this kind of a shape. It looks like the shape of an A. And again, you do another one here for the letter B. The same thing here in terms of basically rearranging the different 093 orientation and things like this. Then you have a letter B, okay? And then also finally the letter C. Letter C, again, you have the different kind of layers, 090, whatever, and you have the letter C. Okay, so these are, the reason why we do this is that we can show that the technique can be used to make a very complex structure, okay? And then also recently we developed what we call the omega stiffeners for aircraft structure. So that means that normally in the aircraft structure, you have many of these so-called stiffeners, and they use to really stiffen many of these stringers or different components inside the airframe. And the stiffener can have the shape of L shape, C shape, Z shape, D shape, and so on. And also one thing we call the hat or the omega stiffener. Okay, so I mean, this hat omega stiffener has a base. It has a base and also have something like a hat like this. So that means that in this configuration, people have to make some kind of a complex mold to be able to do that. But by using the method of 4D printing of composite, we were able to form the shape. You can see that you have a base here, and also you have the shape on the top. And so basically, that's you can make it without a mold. Okay, so these are the applications that we have developed. Now, to have other kind of potential applications, I mean, you know, you can use this technique to do that. It is saying that you can have efficient packaging for transportation. So that means that in this case, if you were to transport something that is bulky, something like a big volume, into some kind of remote location, such as in outer space or into the North Pole, you know, in the kind of remote location, then it would be kind of difficult or expensive to transport something in a large volume. But if you use this kind of technique, you can make a flat structure, and it would be more efficient to transport a flat structure than transport a kind of a bulky volume. And by the time you arrive at the location, then you can cool it down during the, and then the thing spring up to the shape that you want. So that is another kind of thing that you have. Or you have a flexible core for morphing aircraft structure, aircraft wing. That is the case, you can change the configuration of the structure by using that. Or you can have flexible, extensible antennas and solar cell tractable mechanism. So these are the items that we're working on right now. So in conclusion, I would like to say that by using anisotropic properties of composite, one can make engineering structures that can be reconfigured to a desirable shape after the deposition using additive manufacturing. And as such, you can make complex structures without using complex mold. I would like to acknowledge the financial support from the Natural Sciences and Engineering Council of Canada, and also many of my associates and students, Dr. Daniel Roska, Mr. Gil Singh, Ms. Bhargavi Reddy, Mr. Hoàng Vinh Đức, Mr. Xiao Kai, Mr. Heng Wong, and many students in the manufacturing composite courses at Concordia University. And I thank you for your attention.